And here we are. We now get to the fourth quantum number, which has to do with spin, or conceptually at least, it can be understood as due to the electron revolving around an axis, which is merely a conceptual tool because in no real sense have we found that the electron has any extension, therefore it's not really an orb, we would say, that could actually rotate like that. That aside, the way that a particle's spin acts can be understood by thinking about electrons and protons and quantum objects revolving. Because mathematically, this spin acts exactly like angular momentum. It's sometimes called the intrinsic spin because it's not really due to the normal sense of spinning or revolving you might think of, like planets revolving around their axis. So it very much mathematically acts like that, but yeah. So this is definitely one of the places where our intuition is going to fail us in thinking about what it is that's spinning here, right? Spin is just a word that we're using because the thing that we're talking about acts a lot like something spinning, even though there's no real sense, physical sense, that there is something necessarily rotating there. So, putting aside those philosophical quandaries, we're just going to look at the mathematical definition and see how it affects the overall state of electrons and atoms, and then we'll finally get to a full description of an electron in an atom, and then we can start building up larger atoms and elements. So like I said, mathematically, this spin, this intrinsic spin, acts exactly like angular momentum, and so we have this new quantum number, technically two, but really only one is necessary or needed. So little s now is very much like little l that we had earlier, and it gives us the magnitude of the spin of an electron. Same relation as like little l and big L earlier. And then if you think about the projection of that spin on the z-axis, and we get this m sub s quantum number to tell us about the spin along the z-axis. And so it turns out that the little s there is a fundamental property of particles. It, in a very strong sense, defines part of what makes that particle what it is. So it's similar to like the mass of a particle or its electric charge. For electrons, which we're almost entirely going to focus on, I don't even think we talk about anything else right now at least, but electrons, that s value is 1/2, right? It's not an integer. And also for protons, it's 1/2 as well. So s, again, remember, is much like the little l, and m sub s is much like the other little m. So this m sub s can run from minus s all the way up to plus s, right? And in integer steps, so adding 1, minus s, and then minus s plus 1, all the way to 0, and then all the way up to s minus 1, and up to then s. So those are all the possible m sub s values. What that means for an electron then, when s is 1/2, that means that its projection along the z-axis, m sub s, can either be plus 1/2 or minus 1/2. We call those states where the electrons spin up or spin down. And here's a picture sort of the total spin of the electrons, very similar to its orbital angular momentum, and then the projection of that spin on the z-axis. So the value of that spin ends up being just that m sub s multiplied by h bar, so plus h bar over 2 or minus h bar over 2. So this is the spin up state or the spin down state. And so it is a little bit confusing because we use m for two different quantum numbers, and they just have subscripts. Partly it's because they're both due to projections along the z-axis. So remember, m sub l had to do with the projection of the electron's orbital angular momentum along the z-axis. So in a sense, it has to do with the angular momentum projection of the atom overall, whereas m sub s is the projection of the electron spin. So like, remember thinking about an electron like it's rotating. So the axis that it's rotating on, that's this spin value, right? And the projection of that along the z-axis, that's what our m sub s is telling us about. Beyond just being a further value and sort of final value to define the state of an electron, this spin, this spin up, spin down states, they're useful because they also add to the complexity of the energy states, the possible energy states of an atom, meaning that they will affect the atomic spectra of the atom. Exactly like before when we were thinking about the magnetic moment or the magnetic dipole moment of an electron that's orbiting around in this sort of loop, right? We got that magnetic moment. Now we're thinking about just the electron, not it orbiting around the proton, but just the electron, and it's revolving around an axis. But that's still some amount of charge, and that charge is revolving, it's moving, so that's also going to produce a dipole, and this one now is associated just with the electron. And just like when we're looking at the Z1 effect, that dipole, magnetic dipole, can be influenced by external magnetic fields. That's where these different energy states come in, where that dipole is like aligned with the magnetic field, it's anti-aligned, it's somewhere in between there. Those are all different amounts of potential energy, and so they result in further splitting of some of these atomic spectral lines. And if you work out what the magnetic dipole is along the z-axis for the electron, it ends up being this value. Because that m sub s can take on plus and minus 1/2. The only possible magnetic dipole values are plus and minus that Bohr magneton, that constant value that has to do with the charge and mass of the electron, multiplied by h bar. Pretty simple. I mean, getting there is not necessarily simple, but the result is quite simple. Let's then put some numbers to this potential energy business that I was talking about, where we think about a hydrogen atom in ground state that is placed in an external magnetic field, where the magnetic field strength is 1.5 teslas. We're asked to determine the frequency of radiation produced in a transition between a spin up and a spin down state. So just due to the fact that the electron has this spin property, where it's like it's rotating around an axis, it can make transitions between those states, just like it made transitions when we were thinking about just the Bohr model. It would make transitions, say from n equals 2 to n equals 1, n equals 3 to n equals 1, right? Make those transitions. There's now this added transition where it goes from a spin up to a spin down, or a spin down to a spin up. What's the energy associated with that? And then what's the frequency of, say, a photon that would be released if it made that transition? Well, what is that then? This was our magnetic dipole. It's right here along the z-axis. Again, if we go back to the potential energy associated with a magnetic dipole in an external magnetic field, that's in general for our particular dipole along this z-axis. This is what that potential energy looks like. And so it really just comes down to plus or minus or plus that Bohr magneton multiplied by the magnitude of the external magnetic field. Put that external there. So if that's the two possible potential energy states, making a transition from one to the other is going to be, well, the energy from the energy difference between those two states, right? So it's twice this value. And if we want to know the frequency of like a photon with this energy, we can go back to our energy frequency relationship from Planck, and that frequency then is the energy over Planck's constant, and that energy is just that change that we got here for the difference between those states. That's the energy that the photon's coming out, so 2 times that Bohr magneton times the strength of the magnetic field over h bar. Now we finally put some values in. The Bohr magneton is 5.79 times 10 to the minus 5, and that's in terms of electron volts per Tesla. Strange units, but that's what it is. The strength of the magnetic field we were given was 1.5 Teslas. And since we're using this Bohr magneton in terms of electron volts, we should write Planck's constant in terms of electron volts, which was that. Right, so the electron volts, the Teslas go away, we're going to end up with units of 1/seconds or hertz, which is good because that's frequency. Becomes 4.2 times 10 to the 10th hertz. So pretty high frequency. That is also a pretty large magnetic field. One Tesla itself is a pretty darn large magnetic field. So it makes sense that the energy difference and then the frequency of a photon coming out due to that energy transition is going to be pretty high frequency. Even further structure in the atomic spectra comes up due to now interactions between these magnetic moments that we're talking about, these magnetic dipoles, right? Because there was the dipole associated with the electron orbiting the proton, and now we have the dipole associated with the electron revolving on its axis, this spin, intrinsic spin. And these magnetic dipole moments came about because we're thinking about charge moving or rotating. So they're also, associated with magnetic fields of their own, and those magnetic fields can influence the other dipole. But in simpler terms, there's now further energy states that are separated by the difference when these dipoles are aligned. Right? When they're in the same direction, there's particular magnetic potential energy associated with that state, versus if they're anti-aligned. This is actually a larger energy state. That adds another transition that can happen for the electron, meaning you're adding more lines to the atomic spectrum. This is known as the spin-orbit coupling, right? After doing with the dipole associated with the spin of the electron interacting with the dipole associated with the orbit of the electron. And that spin-orbit coupling results in this splitting of these spectral lines. That energy, that difference in those energies is pretty small, so you don't necessarily get to see this splitting in the lines unless you get to a point where you can resolve very highly these lines in the atomic spectrum. So this sort of fine splitting of these lines is then known as the fine structure of the hydrogen atomic spectrum, or the fine structure of the atom's atomic spectrum in general. We're now seeing more and more reasons why the analysis of the spectra of atoms is incredibly useful in sort of verifying or testing our ideas of how the atom works. The fact that we do get these split in the lines and the energy associated with those that we can calculate is the same as the split in that line tells us that this understanding, this model, is quite good. It's working quite well. There's another sort of confirmation of this idea of electrons spin, or having this intrinsic spin. And that came from these scientists Stern and Gerlach. It's a very famous experiment, Stern-Gerlach experiment, where they were essentially shooting atoms that, I think they were hydrogen-like atoms, so they're silver atoms, but they had all their electrons except for one stripped off. And they send those atoms through this non-uniform field and see, well, then you have this photographic plate on the other side, so you can actually see where these atoms are landing on that plate. The classical understanding would say that those electrons can have a continuous range of this spin. It's not discrete, it can be whatever it wants to be. And so as it moves through this field, those atoms would kind of get spread apart, right? The beam would get spread apart according to this continuous difference in the spin of the electron. And so what you would get on the plate is you just get this kind of spectrum, right? Continuous spectrum. However, the result of this experiment was that it wasn't a continuous spectrum, it was just here and here, right? Up here, down here. Those are the marks that you get on your photographic plate in the end. And there's a confirmation that the electrons in these atoms only had two possible spin states. And so when they go through this field, and the fact that it's a non-uniform field is necessary because you need a non-uniform field in order to actually exert a force on a magnetic dipole. Yeah, if it's a uniform field, then you don't get an overall force in the dipole, and so there would be no splitting. Not super important, only more that the fact that that field is set up in such a way that it will split or spread out atoms according to that spin, that electron spin. And as it turns out, there's only two possibilities. That's where, again, we're calling the spin up and the spin down state. One more thing before we start going towards the periodic table is thinking about particles as having this intrinsic spin means, well, we could also think about the proton having this intrinsic spin, like it's revolving around an axis. Again, it's a charged particle, that charge is moving, so there's an associated dipole, and that dipole is, magnetic dipole, is separate from the orbital one, from the electron spin one, and it can actually interact then with the electron spin. So essentially the spin of the proton and spin of the electron results in these magnetic dipoles, and those then can also interact. The energy there is even smaller now than it was with the electron spin and its orbit. Right? That was that spin-orbit coupling. It gave us a spine structure. The energy associated with the proton spin and interacting with the electron spin is even smaller energy there, where they're aligned or they're anti-aligned. But it's there, and you can, if you have enough resolution, then you can see that further splitting of the spectral lines. And this is what's known as the hyperfine structure, due to what now we call the spin-spin coupling. So coupling with the spin of the proton and the spin of the electron. And one place where that is useful is in astronomy, where you can look at that particular emission line that's due to that spin-spin coupling. So like in hydrogen, it's that 21 centimeter line, that's the wavelength of that light. And knowing that that particular emission line is due to the spin-spin coupling in hydrogen means that wherever we see that spectral line, that 21 centimeter line, there's hydrogen there. That's one way of mapping out the structure of these galaxies. So in the left picture, if you just looked at the visible light, then you don't see quite as much of the substructure because there's a lot of gas that's blocking out the visible light from going all the way through. But the 21 centimeter wavelength penetrates much better, and so if you look at just that, you see a lot more of this substructure, fine kind of detail. Some of that stuff about the spin couplings, spin order couplings, useful stuff has useful applications, and giving evidence for our understanding of this model, that it's correct or it works in all these scenarios. It gives us very good predictions that agree with the experiment. But now we kind of want to look at the consequences of the fact that the states are all quantized and they have these particular quantum numbers associated with them, and how that allows us to build up larger atoms, helium and lithium, beryllium, boron, all those kinds of things. We almost have all the stuff we need. So it's just these four quantum numbers are what fully describe the state of an electron in the hydrogen atom. And they have these allowed values, right? N can be 1, 2, 3, 4, 5, whatever. L can be 0 up to n minus 1. The angular momentum projection, m sub L, can be minus L to plus L. And then finally now our spin projection, m sub S, for an electron can only be minus 1/2 and plus 1/2. Spin down, spin up. So take all of that. That describes your electron, and along with what's known as Pauli's exclusion principle, we can start building up atoms. So the exclusion principle essentially says that not only does any given set of these numbers, these allowed numbers, fully define an electron in the hydrogen atom, but in an atom, no two electrons can share all of these quantum numbers, so they can't all have the same quantum state. And that is particularly for our electrons and for spin half particles, half spin particles. Pauli's exclusion principle doesn't apply to all particles, but electrons, protons, it does. Okay, so we're going to go back to now enumerating some of the possible states. To start out with, simplest state, n is equal to 1, right? L has to be less than n, so L can only be 0. M goes from minus L to plus L, so M is also 0. But now we have this additional quantum number, that spin projection, m sub S, can have two possible states. So now that n equals 1, state actually has these two sort of substates, right? Spin up and spin down. And you write the spectroscopic notation, right? S just means L equals 0. P means L equals 1, right? So that's the spectroscopic notation there. and then we're saying how many electrons are allowed in a subshell and then a shell. More terminology here. Electrons with the same principal quantum number, the same n, those are all considered to be in the same shell, and electrons with the same angular momentum quantum number, that L, same L value, those are considered to be in the same subshell. So if you just start enumerating some of these, you start to see how many electrons actually fit in these different energy states. Right? So with n equals 1, you can actually have 2 electrons there. When n equals 2, well, there's subshells, right? Because L can take on multiple values, and you have, the 2s state has 2 possible positions for electrons. The 2p state has 6. So in total, n equals 2, there are 8 possible positions for electrons. Or you could say that 8 electrons are allowed in that shell. And as you might imagine, the larger n gets, the amount of electrons goes up pretty steeply. You're always going to have that L equals 0, M equals 0, but now that spin up and spin down allows for 2 states here. So n equals 3, L equals 0, M equals 0, you still have plus 1/2 and minus 1/2 for the spin projection. There's still 2 possible states for electron in that subshell. When L equals 1, or P, 3p, 6 possibilities. When L equals 2, now since n is 3, L could be up to 2. And D is the letter we use, just means L equals 2. There's 10 possible states. So put all those together, in this energy state, n equals 3, there are 18 possible places for electrons. Or overall, there could be 18 electrons with n equals 3. Do much or have much background with chemistry, you might start to notice some of these patterns where the possible amount of electrons allowed is going up in this sort of recognizable pattern, right? Total electrons in each shell was then like the 2 and 8, then now 18, the next one would be 32. Or in the subshells it was like 2 and then 2 and then 6 and 2 and 6 and 10. Yeah, you might start to notice those number patterns from chemistry. Now that we are going to imagine adding more and more electrons to an atom, it can be useful to think about the electrons that are sort of the last ones in there, right, in the very outer shell. So it turns out that as far as chemistry is concerned, the outer shell electrons, or what are known as the valence electrons, really strongly determine how chemicals are going to bond and things like that. So if we think about what that electron is like in the outer shell, or the outermost shell, then for hydrogen, right, hydrogen just has 1 electron. In that n equals 1, L equals 0 state, there are 2 possible positions for electrons. Right? But hydrogen just has the 1 electron. We're thinking about neutral atoms right now. Same number of protons as there is electrons. So hydrogen, its valence electron state is just 1 electron. 1 spin up or spin down electron. Helium has 2 protons, right? We're just going up in proton number here. And neutral helium would have 2 electrons. So helium fills up that n equals 1 shell. You have 2 possible positions for electrons. It has a neutral helium will have 2 electrons in those positions, spin up and spin down. Then you get on to lithium, right? So now that n equals 1 shell is fully filled, and so we're only writing the outer shell here, depicting the outer shell with arrows for the electrons. So the next shell that starts to be filled is n equals 2, and you get 1 electron. Lithium is 3 protons, so 3 electrons, 2 in the first shell, and now 1 in the outer shell. So that's our valence electron. Then you get beryllium, right, which now 4 protons, so 4 electrons, and that 2s state is now filled, right, because there are 2 possible positions for electrons there. And you can keep going up and up and up, right? So in the 1s and the 2s, there's only 2 places for electrons, but then you start to get to the p states, 2p, right? And now we have 6 possible places for electrons. So now we get up to filling up these sort of spin up and spin down positions all the way up until we get to 8, and then we start over with the new shell. So now, like, just continuing that process, or thinking more about that process of like building up a element by increasing the proton number, right? Because the number of protons defines what element it is, and then having to add more electrons as you go in order to keep thinking about just neutral atoms. So start out with hydrogen, 1 proton, 1 electron. Upper left corner in the periodic table, there's hydrogen right there. And that 1 electron is what you call it unpaired, where that outer shell is not filled. Chemically speaking, that means that hydrogen is very active, right? Because it's just that 1 electron there, so there's space for some more stuff, or it can kind of be left over. So the less filled the outer shell is, the more sort of chemically active an atom will be. And that top row in the periodic table is n equals 1. So when n equals 1, L can only be 0, but you have spin up and spin down, so there's 2 possible states. So we go from hydrogen with 1 proton, 1 electron, to helium, 2 protons, and now to be neutral we'll have 2 electrons. And in that 1s state, there's 2 possible positions for electrons. So when you have the 2, well, you have spin up, spin down, that outer shell is completely full, meaning that helium is chemically inactive or inert. Like it doesn't want to share its electrons because they're already paired up. It's also called noble. Now go from helium to lithium, right? Now we're going down to the second row, so n equals 2, and lithium now another proton, so 3 protons, now 3 electrons, and that 1s state is filled, up and down electron there. The 2s state has 2 possible positions for electrons, so lithium only has the 1, meaning that it also has this unpaired electron in its outermost shell, and it's also going to be very chemically active, like hydrogen. So then you can, continue along, think about beryllium. Beryllium is 4 electrons, or 4 protons, so 4 electrons. And now in that 2s state, there are 2 electrons, but the n equals 2 shell can have up to 8 electrons overall. So 2s is the subshell, but the full shell is just 2, which you get 8 overall electron positions. So beryllium still has a bunch of open positions kind of for electrons. I mean, it's still going to be fairly active. It's less active, say, than lithium, because it does have 2 electrons in that shell already, but still fairly active. And you keep going along. On the other side, then, maybe you think about finally getting to neon. Neon is a 10, I believe, so 10 protons, going to be 10 electrons, and now that first shell, 1s, right, was already filled, 2 electrons there. The second shell, n equals 2, has 8 possible positions, right? So by the time we get to neon, we fill up the first and the second shell entirely, meaning its valence shell is full, meaning it's going to be chemically inactive. It's not going to want to easily share those electrons. This is why the periodic table is laid out the way it is. That helium and neon are similar because they both have fully filled outer shells. Helium, lithium, sodium, potassium, all that first column act similar because they only have 1 electron in their outermost shell. So this is why the periodic table is laid out in these columns like this, and the elements in the same column have similar chemical properties, and then the rows are just our increasing principal quantum number, increasing n. And this is how we can get an understanding of the chemical properties of atoms based on our analysis of Schrodinger's equation and the results of the solution to Schrodinger's equation for that Coulomb potential, and the fact that those results were all indexed by these different values. And that, along with Pauli's exclusion principle, allows us to kind of imagine how we build up this periodic table. It should be noted that the energy of any of these states is not entirely specified by n, by the principal quantum number anymore. Partly because as you are getting larger and larger atoms, it's not just the single electron that is now interacting with the charge in the nucleus. If you have a hydrogen-like atom, remember, you can have any number of protons in the nucleus, but you only had 1 electron. You had to take all the rest of them away, strip them all off. When we're talking about actually filling all these electron shells, that's just not the case, right? There's all these electrons there, and they actually are interacting with each other as well, right? They each have their own electric charge, they produce electric fields, there's electric potential associated with them. And so it turns out that the energy states is not only just going to be about n now, that there are some different variations that come in due to the electrons, all these extra electrons. Here we see some energy level diagrams. So when you think back and we look at the Bohr model, we had this same kind of energy diagram, but there was pretty much just the one sort of column, right, where n could increase. So it could be 1, 2, 3, 4, 5, 6, 7, right? So we got that. That's still here. It's just now with Schrodinger, we have all these other substates within any of those n values, at least for more than n equal 1. So when n is equal to 2, then we could have 2s, that's one subshell, or 2p, another subshell, or the full shell is just that n equals 2. Both of those together is the n equals 2 shell. Or up to n equals 3, there's s, p, and d subshells. So this is kind of another way of picturing how do you build up these atoms where you're filling these shells with electrons. So each of these little arrows is representing an electron, where pointing upwards is a spin up electron, pointing down is a spin down electron. And hydrogen just has the one electron, so put it in there, might as well call it spin up. Helium, put another electron in there. It can't have the same quantum numbers as that first one, so the only option there is that it's a spin down versus the first one that was spin up. But now that 1s state is completely filled. Going on to lithium, another electron now is going to go into the 2s state. And so you're just filling up the energy levels of these atoms. All the way to a larger atom like iron, you see has all these states filled, and then some of the higher ones are only partially filled. And here you start to see where it's not quite as easy as I was making it out to be, where you're just filling up the shells as you go, right? n equals 1, n equals 2, n equals 3, and fill up all those. Because, like I said, there's actually differences that all these electrons in the atom together are adding to the energy of each of these states. And particularly here, it turns out that the 3D, n equals 3, L equals 3 energy state is actually higher than n equals 4, L equals 0, 4SC. So that 3D energy level is actually higher than the 4S energy level, meaning that that 4S energy state is going to get filled before the 3D state is. So the way that you actually fill all these states depends on their actual energies, or the energy of that state. But another way of thinking about the electrons in atoms and how that influences their chemical properties. Are these outer shells filled? Are they unfilled? Or how full are they? That kind of stuff. So now we have a picture that's much more complex than it was for Bohr. When you think about the Bohr model, we just had an electron, it was orbiting the proton at some radius, and those radii were quantized, so it could only be, say, here or here or here, right? But there are all these circular orbits, pretty simple. So when you had a transition, the electron was just going to go from one of those to the other one. If it drops from an outer one to an inner one, that's a decrease in energy, and that energy leaves as a photon, which is equal to the energy of that transition. If it goes from an inner to an outer, that means it would have absorbed some energy and pushed it up. So pretty simple. Now though, that we have our Schrodinger model and all of these principal quantum number states, these n equal 1, 2, 3, 4, those states, they start to have all these substates. And so you have much more complex transitions that can happen. And in fact, there's actually something that happens when you're talking about a transition having to do with the conservation of angular momentum, is that you get these sort of allowed transition versus forbidden transitions. That basically means that the allowed transitions end up being ones where little l, the orbital angular momentum quantum number, where that changes by 1. So remember, these s, p, d, f, those are just enumerating different l's. S is L equals 0, E L equals 1, D L equals 2, F L equals 3. So the allowed transitions in these diagrams are the ones that go one column left or right. And that's the allowed transition because L is changing by 1. Other transitions are what you call forbidden. And the words allowed and forbidden is a little bit much maybe because the other transitions are actually possible. In transitions where L is greater than or less than 1, right? It could be 0. You could go from an S state all the way to an F state, right? L goes from 0 to 3. That's still possible, it's just very unlikely. Right? Everything we're dealing with now is probability. And so the transitions that are much, much more likely are when L changes by 1. So you go 1 column left to right. All right, now we're just going to look at a couple of applications or uses of some of this information now. One is in the production of X-rays. If you want to produce X-rays, you can do this by basically shooting electrons at some target, and in this case they're showing the target is a tungsten. You get some radiation, electromagnetic radiation, due to the electrons decelerating. I think if you think back to your electricity and magnetism, if you have an accelerating charge, that will change its energy, and so that change in energy moves away as electromagnetic radiation. You produce some electromagnetic rays that way, but the X-rays are actually produced by the electrons that interact with the tungsten atoms, and some of these electrons are actually able to penetrate sort of into the tungsten or into a tungsten atom and knock one of the inner shell electrons out. So there's even more terminology and labels that come involved, like don't worry about that. The important thing is that these electrons that we're firing at the tungsten are sort of diving into the orbital and knocking out an electron in a much lower level. So it kind of leaves this like hole within the atom so that one of these outer shell electrons now can make a transition all the way down to that inner energy level. And when you're dealing with atoms that are fairly large, that energy transition can be very large. And when that electron drops down to this now open space sort of well below it, that energy is in the range of X-rays. Right? So again, remember, think about the energy difference in that transition, and then using Planck's relationship that E equals energy equals the frequency times Planck's constant can tell you the frequency of that radiation, and you can show that that frequency is in the X-ray range. So that's how you can produce X-rays. And you probably know some of these applications. X-ray for medical applications, dental X-ray for security applications, I guess you'd call, for X-raying backpacks or bags or something going through the airport, something like that. So the X-rays that are produced in that little tungsten setup can be then directed towards something, and what you end up getting or producing in X-ray images is the sort of shadow that these X-rays produce. So when they go through material, they'll be able to penetrate more or less depending on how dense the material is. And so you get the X-rays that came through, and the more intense places that you see, that was pretty low density material. A lot of those X-rays made it through. Versus very dark areas where not many X-rays made it through, that's very dense material. Things like the metal in here are pretty dense, and so they look very dark in these X-rays. And then the last application to talk about here is lasers. The term laser started out as an acronym, but I think at this point has basically been accepted as a noun in itself. If I remember correctly, the acronym is Light Amplified Stimulated Emission of Radiation, but laser sounds way cooler. So anyway, what is a laser then? How do you produce it? Well, one level of thinking about that is just imagining or thinking about our energy levels for atoms, and if you are able to get some material, either gas or whatever the material is, but you're able to set it up in such a way that the majority of the electrons in that material are not in the ground state, they're in some excited state. And that's what they call this metastable state. So they're there, but there's room for them to drop down. So if you get this setup of this metastable electrons, and then you have a photon pass by that atom, and that photon has an energy that is the same as that electron energy level, right? This energy is the same as the energy of that photon, then that passing photon can stimulate an electron to drop down. And since its energy is the same as that energy transition, then that one photon now just stimulated a second photon that is the same energy as itself, so has the same wavelength, the same frequency, and is in fact going to be in phase too. As those energy photons are passing through this gas, they keep stimulating these electrons to drop down and produce all this light that is in phase, and it has the same energy, the same frequency, the same wavelength. So what you get out is a bunch of photons that are coherent, same phase, same frequency. How do you make this metastable state? Well, there's a lot of ways to do it, but just to point out one way, sort of the simplest way of thinking about it, is that, again, you just have this material that you're going to work with, that's your lasing medium, I think they call it, and the electrons in those atoms have these energy levels, just like we've been talking about, but it turns out that the time that an electron will generally sit in any of these states is different. It's not the same for each of those energy levels. So if you have a material where the energy state, say, of an electron being at this upper energy level, right? Look at this bond diagram here. An electron being that upper energy level is going to pretty quickly want to drop down to the middle level there. But that middle level actually has a pretty long, relatively long lifespan before it wants to drop down to the ground state again. So if you have a material like this, then you basically pump energy into this material, and you can do that in a number of ways, but all you're doing is getting the electrons excited, so they go up to this higher energy level, this upper energy level. Pretty quickly though, they drop down to that mid-level, but again, that mid-level has a pretty long lifetime, so a lot of the electrons are going to be sitting at that middle level. And that's exactly what you want for the metastable state. If you're continually pumping energy into this material, then you're going to get a lot of these electrons just kind of hanging out in this middle state, in the metastable state. And then some of them, when they do drop down, will start to release photons where their energy is equal to that energy. And that's why in a laser, you generally have a cavity where you're bouncing the light that's in that cavity back and forth. So that sort of initial photons that get released in these metastable states are now going to start stimulating all the other states to drop down. And then you get this avalanche effect where you end up with all these photons that are coherent. So just to remind you, coherent light is light with the same frequency, same wavelength, same phase. And if you recall, when we were doing optics, having coherent light made things much easier in general. So when we're thinking about like interference and diffraction, right, the ability to even study those properties or study those phenomenons required coherent light. Or if it didn't require it, it was made much easier to look at by having coherent light. And yeah, like I said, lasers have applications all over the place, medical applications, industrial, scientific. One of those that's conceptually pretty easy to understand, even though we don't really use compact discs that much anymore. Anyway, you probably know what a CD or at least a DVD or Blu-ray disc is. They are essentially information storage devices that utilize lasers in order to read back that information. So you look up really, really closely, sort of like side on to one of these discs, you cut through a cross-section of one of them, and it's just covered these bumps, right? Bumps and dips there, or pits and bumps. And what you do is, well, if you shine laser light into that, then depending on if it hits a bump or if it hits a pit, it's a slightly longer distance to go down to the pit and then back. And so you can set it up in such a way that if it, say, hits that bump and comes back, it's going to interfere constructively. But if it goes that little bit of extra distance to the pit, comes back, it's destructively. So just shooting laser light at that disc can tell you if you're on a bump or a pit by having a sensor that sees the light that comes back and see if is it bright or dark, is it constructive or deconstructive. And as long as you can say, yes or no, off or on, 1 or 0, you can encode digital information. So this is one way of encoding information on a disk, and depending on the wavelength of light you're using, the wavelength of the laser, you can make smaller and smaller features, or the feature size, the overall size of these pits and these bumps can be smaller and smaller and smaller, meaning you can encode more information on the same size disk. So that's why a CD was something like, I guess, 0.7 gigabytes, whereas a DVD uses, well, the CD was using 780 nanometer light, DVD uses 650, shorter wavelength, higher frequency, can illuminate smaller areas. You can compact things down, fill up almost 5 gigabytes, and Blu-ray utilizes, looks like about 400 nanometer wavelength light, so even smaller features are possible, and you can encode something like 25 gigabytes. Alright, and then just to end on some other applications of lasers, from like industrial applications for cutting metals. You can cut all kinds of stuff with lasers. And the fact that the light is coherent means that the energy that's produced in the source of the laser is allowed to stay focused and actually go to that point. If it's not coherent, then it will tend to spread out a lot. And so that energy spreads out a lot. You don't get to be able to focus that. With a laser, you can. This picture in the upper right is, what is the term? Oh, I forget the term right now. But ground-based observatories, like telescopes, you're always seeing through the atmosphere. And you can actually use lasers to kind of assess what the atmosphere is doing, like how turbulent it is above the observatory. And if you know that, and kind of a map of what that turbulence looks like, then you can adjust for that. You can account for that in the images you get, and so you can have a much clearer image from the ground-based observatory because the lasers allow you to sort of map out the atmosphere above you. And then just straight up, scientific applications, easier to make optical measurements than many other scientific applications. I think the bottom there is showing part of the process of laser eye surgery, the LASIK. Well, that's chapter 8. So I will see you in class or see you on the internet somewhere next time.